So I had started working on this one before I had realized my microphone wasn't working. So I'm just going to leave my writing and just kind of explain what I'm thinking on this one. If I have any corrections or comments, I'll put it in the description below. But I don't, just in the interest of time, I don't really want to repeat myself here. So a wheel is mounted on a horizontal axle, light strings attached to the wheel's rim and wrapped around it. Two students are when the block is released from rest begins to fall, the wheel begins to rotate with negligible friction. Students are discussing how different forms of energy change as the block falls. One student says the kinetic energy of the block increases as it falls. The second student says this is because the gravitational potential energy is converted to kinetic energy. The students decide to test whether the decrease in gravitational potential energy is equal to the increase in the block's kinetic energy from when the block starts moving to immediately before it reaches the floor. So we want to know about the decrease in gravitational potential energy, and we talk about the increase in the block's kinetic energy. So we want to design an experimental procedure that the students could use to compare the increase in the block's translational kinetic energy with the decrease in the gravitational potential energy. So I want to record, ultimately I need to record 1/2 mv squared and mgh, or I need to somehow compute those things. So what I decided to do was the mass of the block, I need a scale. Height of the block above the ground, I need a meter stick. Speed of the block, v, I need a motion sensor. Now, why did I pick a motion sensor? I was debating whether or not you should just use a camera, but because the speed is changing, I figured a motion sensor would be more accurate. It's hard to capture. You can capture the height with a meter stick, but you just have to be a very high-speed camera to sort of estimate the velocity because it's accelerating downward, so it's a little bit tough to keep track of its velocity at any given moment in time. But you certainly could do that instead. And then I was going to position a camera here that kind of observed it falling. Okay, even with the motion sensor. Now, careful when you're using a motion sensor. You do have to position it underneath it because motion sensors can only do it as it's coming or as it's going. Okay, so I have a camera here observing it that whole time. So I said the steps were to weigh the mass of the block, to set up the meter stick being behind, set up the meter stick, my handwriting is terrible, behind the block and camera facing it. Position the motion sensor directly below the block. Release the block and record the height from the camera and video and velocity from the motion sensor data. And repeat from the same height 3 times. This is where we're going to handle the experimental uncertainty part. We're going to repeat it a few times at the same height. I'm also going to change the height of the release point and repeat that 3 times, just to vary, just to make sure. It's nice to vary something, make sure it's not like kind of just specific to the height or there wasn't an issue with that. Okay, and then explain how the students could determine the kinetic energy of the block immediately before it reaches the floor using the quantities we indicated. You want to just say specifically how you're going to calculate it. I'm going to record the maximum velocity from the motion sensor data as v. Why? Because the maximum would tell me how fast it possibly was. Because the motion sensor data is going to be a bunch of velocity. You want to grab it, the largest one, because that presumably is right before it hit. And then you have m, and then you would just say ke is 1/2 mv squared. All right, this one, we'll kind of do this one. So the graph represents the change in the gravitational potential energy of the block wheel earth system and the translational kinetic energy gained by the block as the functions of the falling distance. On the graph, draw a line or curve to represent the rotational kinetic energy of the wheel as a function of the block's distance d. So in this one, what you have to think about is the reason the energies don't line up is because this thing is spinning, right? Or at least, like as this thing falls, it gains kinetic energy, the block does, but the wheel gains rotational kinetic energy. And so what you want to think about here is, by conservation of energy, if there's no work on the system, which is a fair assumption, except for like air resistance and friction, those are only possible things. We want to say the total energy ought to be 0. So I need to pick a value. I know that it's not spinning, so it starts at 0. And then the total energy is to add to 0. So this is going to be something like here, like this line. And that way, everywhere the energy adds to 0. Okay, like this is like a little bit like almost 0.25. This is 0.15. That adds to 0.4, and that's negative 0.4. So you want these two you just want to pick it that way so that the vertical values would add up. Like this and this, 2 and 1 add to negative 3, and then that and that add to negative 2. This adds to 2, etc., so that the total energy stays 0 the whole time. Okay, so this one I had already done the straight line here. And I was just illustrating as they're doing the measuring the angular velocity as it falls to determine the rotational kinetic energy. and they want to they graph kinetic energy as a function of omega squared. So here, what you want to do is you draw the line of best fit, and then you say the kinetic rotational energy is equal to 1/2 I omega squared. Now they plotted on the y-axis, they plotted Kr, that's your y value, and then on the x-axis they plotted omega squared, the x value. So the slope has to be 1/2 I, right? So then I just picked 2 points on here and I estimated the values, and you just pick 2 points along your line. Doesn't have to be specific, like your number is going to be a little bit different than mine, but just make sure it's 1/2 I. So I got 2 over to 35 when I did my numbers here, and I got 0.057. And that was it.